In this segment, we are going to discuss a problem from kinematics, and this is related to the cylindrical coordinate systems. The problem goes like this. There is a sprinkler. This orange color thing is a sprinkler which is able to rotate actually once the water flows out of this, and the water is coming out of the sprinkler at an angle of alpha, which is 60 degree with the horizontal, at a speed of 3 meter per second. Okay, so the speed of water is 3 meter per second at which it is coming out, and the radius of the tip of the nozzle from the center of rotation is r, which is 3 meters. So this is the distance of the tip of the nozzle, and then yeah, it's rotating at a constant angular velocity, so omega is constant, which is 2 radians per second. So in this position, this condition, we are supposed to find out the velocity and acceleration vector of the water particle that is coming out of this nozzle. Now, for solving this problem, it's obvious things are very axisymmetric, so rotating at a given radius. So it's very intuitive to think about the cylindrical coordinate system, and we can actually um, uh, assign the vector r to the water particle, and we can actually write this as r e r plus z e z. Okay, so that means the z-axis is in this direction, z-axis is in this direction, and a radius vector is given by the RER component. Okay, so in that, um, if we write the radius vector as this, obviously the velocity vector will be given by r dot, which will be nothing but r dot er, and plus r er dot, sorry, er dot plus z dot ez. Okay, now these two expressions are coming because of the differentiation of this term, and here both r and er are varying. So r is the radius vector of the particle, which is changing every instant. Okay, and then if we differentiate once again, we shall get the acceleration vector, which will come out to be, I'll directly write it now, r double dot will come out to be r dot double dot minus omega square r. You know how to differentiate now. Er, so these are in the direction of er, plus r theta double dot plus 2 r dot theta dot, so this is in the e theta direction, plus z double dot ez. So this is the acceleration. Now in order to evaluate these values as numerical vectors, so we have to evaluate each of these parameters. For example, let's consider the related to r, everything related to r. Okay, maybe this one, so related to r. Now r dot is equal to what? See, this velocity is coming out of so I'll draw it here. So this velocity is at an angle of 60 degrees, So this direction is v cos 60 degree, and this one is v sine 60. Okay, now this is nothing but your r dot. Okay, and this one um, will give us the I'll say here, so z dot. Okay, so this is z dot and this is r dot, and now we are in a position to evaluate. Let me do one thing. I'll start from r itself so that it will be complete. So r is equal to 0.3 meters. R dot is equal to v cos 60, it is 3 times cosine of 60 degrees, is equal to 1.5 meters per second, and the r double dot is 0 because it's coming out at a constant velocity and there is no change in velocity. That means water is coming at a steady state. Okay, now then let's talk about say theta direction. Okay, now um, theta dot is omega, and it's given to be 2 radians per second, and about theta double dot, it's 0 because we are given that there is no angular acceleration of the rotor. And now so that's what about theta. And if we come to say z, we have z dot is equal to uh, 3 times sine of 60 degrees. This is equal to 2.6 meters per second, and z double dot is equal to negative of 9.81 meter per second square. Okay, because it's the gravity is acting downwards. Okay, now with these values, now we are in a position to calculate say the velocity and acceleration. Then now what will be the velocity? Vector will be so r dot, so this is r dot, so 1.5 er plus then er dot, so r is 0.3 times er dot is your theta dot. Let me not write here, I'll write it here. So this er dot is equal to theta dot e theta. Okay, so that means theta dot is omega, so right, so theta dot is omega, so we will write here 2 e theta and plus z dot is this one, which is 2.6, right? So 2.6 e z. Fine. So this is your velocity vector. I'll write it here again. So v is 1.5 er plus 0.6 e theta plus 2.6 ez meters per second. Now exactly in the same way, if you want to calculate the acceleration vector, so acceleration will be say here r double dot, it's 0 minus omega square is nothing but theta dot square it's 4 times r is 0.3, so 0.3. So this is the first term times er plus r theta double dot. R is again 0.3 times theta double dot is 0, okay, and then plus 2 times r dot. R dot is 1.5 times theta dot is 2, okay. So this is e theta plus minus 9.81 easy. So implies, I'll just write the final expression as say minus 1.2 er plus 6 e theta minus 9.81 easy. So these are our final expression for the acceleration, and this is for the velocity, and this is in meters per second square. Okay, so this is how you should solve the problems related to the cylindrical coordinate system, starting from the basic expression for the position vector. See you in the next segment with another problem.